All right, thanks a lot. Is the microphone okay? Sounds okay.
I'm not sure if we can hear you.
Oh,
Can you turn it on?
I did just turn it on.
yeah.
Is it okay now? Okay. Yeah, so thanks for the opportunity to speak. And happy birthday, Jeremy. So I'm going to talk about some joint work with Chiranjib Mukherjee on stochastic heat equations and Cauchy distributions. And so I'm acutely aware that I stand between you and a beautiful afternoon in a beautiful city with beautiful friends. So I'll try to keep this a little bit light and hopefully interesting. So let me first introduce the model that I want to talk about. So this I want to start out with sort of a notion of general stochastic heat equations, which of course in certain cases are closely related to KPZ and then can sort of branch beyond that in various ways. So in general, I'm just going to consider something like dtu is Laplace u plus sigma of u times c. So here, u will be a function of time and space. T will be real valued. X will live. So to keep it general, I'm going to call it base x, script x here, which will be either RD or TD. Actually, for the results, I'm going to say this is sort of far too restrictive. That you could have a very general state space here, but for concreteness, let me just say we're going to work in RD or TD. And then C will be a Gaussian noise that is white in time. And then it could have quite general covariance in space. Okay, so the expectation of CTX and CT prime X prime will be a delta of T minus T prime, and then some R of X minus X prime. And for concreteness, let me say R is compactly supported, and R equals delta, okay, and D equals 1. So I want to be able to solve this equation. So if I'm in higher dimensions, then I better take R to be kind of colored somehow, but in D equals 1, space have white noise is okay. So if you want, you can just pretend that I'm only talking about D equals 1 and R is delta, and then you'll still hopefully, well, it'll still be interesting. Okay. So, and then this sigma, so this will be a general nonlinearity. This is mostly for motivation, so I'm going to specialize this sigma quite quickly. But just to kind of review some usual choices of sigma. So for some examples, so if sigma u is just identically equal to some beta, we get the Edwards-Wilkinson equation. And this has Gaussian solutions, so we understand this entirely. Right? So that's sort of very simple. We could also take sigma of u to be beta times u, and so this is the parabolic Anderson model, just the exponential of the KBZ equation. And of course, let me just introduce some notation. So as everybody is, well, as most of us are aware, so this multiplicative stochastic heat equation, the solution is the partition function of a directed polynomial. Okay, so if I specify initial conditions, so if ut at some time minus capital T and x is identically equal to 1, then ut of T and x is going to be the expectation with respect to an auxiliary Brownian motion started at Tx of the exponential of the integral from minus t to little t of psi s xs ds minus 1/2 beta squared r of 0 t plus t. Okay, so this is just the partition function of the directed polymer. Yes.
Isn't that usually referring to the noise doesn't depend on time?
Oh, okay, so I have been told that historically this is sort of, I think historically this is actually what it was referring to, but I agree that maybe the term has changed. So let me not get into that argument, but we could also call this the multiplicative stochastic heat equation. But I think the original PAM was for actually space-time noise. But, anyway, yeah, so this is the partition function of the directed polymer, and then the log solves the KPC equations. So if we go from the Gaussian to this sort of multiplicative stochastic heat equation setup, we're really kind of changing two things, right? So we're changing the behavior of sigma. So this is flat and this one's sort of linear, and so we're changing the behavior of sigma both at 0, right? So this one has a 0, right? And we're also changing it at infinity, okay? And so there's been a fair bit of work in kind of recent years about how the behavior of u at 0 and infinity sort of affects the behavior, right? So other popular choices are sigma of u is square root of u. So this gives super Brownian motion. So this is a model for branching random walk. Or sigma of u is square root of u times 1 minus u. So this is related to the voting model. So the asymptotic behavior of sigma sort of far from 0 and close to 0 are different in all these regimes. And so kind of the motivation of the present project is to sort of tease apart, to give kind of another example of this, and to tease apart the behavior, especially interpolating between these two models, right? So, so today, what I want to discuss is sigma of u is square root of 1 plus u squared, right? So we think of this as kind of a looking like Edwards-Wilkinson close to 0, right? So it doesn't have the 0 at 0 that PAM does. But then at infinity, it's sort of linear, right? So it looks like PAM at infinity, right? So this is looks like Edwards-Wilkinson close to 0. And PAM at infinity. Okay, so that's what I want to talk about today, roughly. So before I get to that, let me review a little bit about how this parabolic Anderson model behaves in various dimensions. So if we think about the parabolic Anderson model, there's sort of two competing effects in this equation, right? So one thing that happens is the Laplacian term tends to sort of smooth the equation out and make it more regular, more sort of smooth. And then the other is this multiplicative noise term, right? The multiplicative noise term tends to sort of amplify large values of the noise, right? So if the noise is sort of very large for a certain amount of in a certain region, then the solution will sort of be very large because the noise is sort of getting multiplied by itself. And so these effects sort of compete, and which one wins sort of depends on the dimension. Okay, so what is true is that there is a beta critical, which depends on the spatial domain, such that so if beta is greater than beta critical, then for any fixed t, u capital T of Tx is going to 0 as in probability as t goes to infinity. So this is when we have strong noise, the noise sort of wins, and so the solution becomes sort of very, very intermittent. So you say, why is going to 0 corresponding to intermittent? Well, you have to remember that this thing has excitation 1, and so if it's going to 0 in probability, that means that to keep excitation 1, it has to have very high peaks sort of occasionally. So here, this is the solution is being very irregular, right? Yes, I start with plot. Yeah, so this is my notation. So this u capital T is starting at 1 at minus. And if beta is less than beta c, then ut of tx is converging in probability as t goes to infinity to some non-trivial random variable, right? In fact, it actually converges as an entire space-time process to a non-trivial space-time stationary solution. Okay, so in this case, if everything goes to zero, in this case, if the noise is weak enough and the Laplacian sort of wins out and we get enough averaging, that we get a non-trivial space-time stationary solution to this parabolic Anderson model. Okay, and then, so I wound you all up here with the space transition. Actually, in a lot of cases, there is no phase transition. So if d is 1, actually if d is 0, 1, or 2, then beta critical is 0. Or if x is the torus for any d, if x is RD for d at least 3, then beta critical is between 0 and infinity. So this weak noise phase only exists on the whole space in high dimensions. Okay.
So beta critical also depends on your R.
Yes. Okay. Okay, you scale R, but you're sort of scaling data. Okay. So now I want to talk about this case, right? So what's different here, right? And so actually, I won't be able to consider this particular choice of sigma directly. Instead, I want to consider sort of a closely related equation, right? So so what I'm really going to talk about today is a related equation, which is dTv is plus v plus beta times v times c plus alpha times eta. So here, alpha and beta are non-negative real numbers, and eta is let me say eta and c are IID. So I'm going to consider two IID noises, one multiplicative and one additive. Okay, so if I'm in this, if my noises are space-time white noises, then this is the same as choosing this value of sigma, right? Because this is just a Pythagorean theorem for Gaussian random variables. But in general, it's not quite the same, but it at least should look similar. Okay, so I'm going to look at this, what we call this. So this is, we call this the AMPHI, the additive multiplicative stochastic heat equation. So we have this multiplicative noise and the additive noise. And now I can state a theorem about this object. This is a joint work with Chiranjib Mukherjee. So there's two parts. So for any beta greater than 0, if we start this guy at so we'll set this guy at time minus capital T with initial data 0 in this case. We don't need to set it at 1 because we have this Gaussian noise that we keep adding in. So we don't need to set it at 1, we'll set it at 0. Then for any fixed positive time, its solution converges as capital T goes to 0 to a non-trivial space-time stationary solution. Which I'll call V tilde. Okay, so we always have a space-time stationary solution here. And then part two is that if beta is bigger than beta critical, so this is the same beta critical as for the PAM, but if beta is bigger than beta critical, then for any x1 through xn in a spatial domain, and any coefficient C1 through Cn, which are non-negative, with the sum of the CIs equal to 1, then the sum from I equals 1 to n of Ci times V tilde of Xi, this is distributed as a Cauchy random variable with parameter alpha over beta. Okay, so this is an exact formula for any positive linear combination of the stationary solution. Right?
Alex,
Yes.
does it depend on your initial data, 0?
It doesn't really. So if you start with something else, if you start with basically anything that goes to 0 under the heat equation, then it'll converge to the same thing. Actually, it doesn't even need to go to 0. It needs to be like bounded under the heat equation. We didn't say the exact condition, but yeah. Okay, so this is the result. All right, so
Are you assuming alpha bigger than 0 or?
oh, sorry, yes. So I need what I stated here is correct. Right? So alpha, if alpha equals 0, then this is a Cauchy 0 random variable, which then that's just the PAM, which then converges to 0. So you just think of the Cauchy as kind of a generalization of 0. Okay, so I don't know. I think this is a little bit nuts because we have this exact formula for certain statistics of this invariant measure, but not all of them. And we don't need to be in the space-time white noise case, right? So any covariance kernel R, we still get these Cauchy statistics. And so if you'll forgive me, I don't really have a good explanation for why this is true. So instead, I think I'll prove it for you, right? So I'll try to give.
If you look at a different set of C's, marginally it's still Cauchy, do you have anything about the time loss?
No. So that's the weird thing. So maybe somebody has an idea, but yeah. So any positive linear combination will be Cauchy, but then yeah, 2 point statistics we don't.
You don't see the connection to Gaussian if you send beta to 0.
If I send beta to 0.
So it just doesn't commute, right?
Right. So if beta goes to 0, then okay. So I think right. So I needed beta greater than 0 here. So if beta, in the case when beta is bigger than beta critical, then the PAM isn't even going to have an invariant measure. Right? So it's not really Gaussian. I mean, it is always Gaussian, but it's flowing. The variance is flowing out. So it's. Okay, so let me give a quick proof of this, of part 2. So part 1, there's some. Well, part 1 is sort of more technical, but less interesting. But part 2, I can give a quick proof. So the idea here is to prove this is to basically use the Duhamel formula, right? So we're going to think of this. We're going to think of this PAM as a linear. We're going to write the propagator for the linear part of the equation, and then add in the additive part, just like in the we'll just write in the Duhamel formula. So to do this, we'll define z of tx sy to be the Green's function for the parabolic Anderson model. So we have the heat cuddle here, and then we have the expectation of a Brownian bridge from Sy to Tx of this polymer thing. Okay, and then we can write the Duhamel formula. So B capital T of Tx is alpha times the integral from minus t to t of the integral of z Tx Sy eta Sy dy ds. Okay. And at the same time, ut of Tx, since u starts at 1, we just integrate the Green's function over the space, right? So this is just the integral of zt Tx Sy dy. Oh, sorry. Let's see, this is not s, this is minus. Okay, so here I'm just integrating the Green's function. And both of these guys are martingales in capital T. All right. So if we think of capital T increasing, these are both martingales. They're adapted to the same filtration. And so we've got martingales. We can try to compute the quadratic variation, right? So the quadratic variation, so this is a simple exercise in stochastic analysis to compute both of these quadratic variations. So if we write this quadratic variation in P, what we get is beta squared times this double integral of r of y1 minus y2 times z of Tx minus Ty1, z of Tx minus Ty2, dy1, dy2. So this is for u. And then it turns out if you try to compute the quadratic variation for v, you're going to get almost the same thing. So this is going to be beta squared over alpha squared times d of the quadratic variation for v. Yeah, and so v is easier, right? V is just a stochastic integral, right? So you can just compute the quadratic variation of that, and then for u, you need to know the quadratic variation of z, but that you can get from this formula for z.
R is the correlator of psi?
R is the correlation function of psi. Yeah. But it's also for eta, so they have the same correlation function. That's what it can be any correlation function you want, but it has to be the same. Okay, so we've got okay, so that's one thing, and then we also want to know the quadratic covariation. Well, but that's quite simple because here the quadratic variation is only coming from eta, and here it's only coming from c. They're independent. The quadratic covariation is 0. Okay, so that means that if we look at alpha over beta times ut of Tx and Vt of Tx as a function of capital T, this is a time change of a standard two-dimensional Brownian motion. And then we need one more We need one more ingredient. So we know a couple more things. So first of all, ut of tx, this goes to 0 as t goes to infinity, because beta is bigger than beta critical. And ut of tx is non-negative, right? Okay. So I'm doing the 1-point case here, but you can see if you have all positive c's, then you can do the same thing. And you'll see that ut is always non-negative. Right, okay, so then if we think about what our time change has to be doing, so we have a 2D Brownian motion. It started here at alpha over beta, comma 0. Yep. So we have a 2D Brownian motion. The first coordinate starts at alpha over beta, and then it has to be going to 0, right? It can't have a cross 0. So actually, so the limit as t goes to infinity of vt tx is the exit point of a 2D Brownian motion from the right half plane, right? And then if you look on page 12 of Evans, this is Cauchy alpha is a beta. Okay, so that's where the Cauchy statistic comes from. I think it's probably a good time for lunch. So let me just mention that that we actually have somewhat more precise results. So I mentioned this beta critical, right? So this beta critical on dimension 2 is equal to 0. But as because we haven't heard about it in this conference yet, you can actually blow up beta critical around 0 by a kind of a log correction, and you can get sort of the same thing in the well, what's technically supercritical in that case. So it's related to the critical stochastic heat flow for those people who know. But I think I'll stop there, and thanks for your attention.
Is this just for dimension 1? Because you're ending up with your 2D Brownian motion.
No, this works in any dimension. So the two dimensions here are u and v. So you have two martingales. Yeah.
If you look at the set as a function of tx and hy, it can be factorized as a product plus small correction. So there is a random value which depends on tx and another sy and Gaussian kernel. So can you use this to get this result?
That is a good question that I have not thought about the answer to. Yeah, somehow we need very little about z here. It's really coming from sort of the martingale structure and sort of the correlation between them. And we're getting kind of an exact result, so it's not clear exactly how this kind of approximation would help, but I'll definitely think about that. Yeah.
It's crucial that the correlations are the same for the.
Yes, yeah. If they're not the same, then there's nothing. Yeah, I mean, it's probably not exactly Cauchy in that case. Yeah.
Do you know any explicit examples which have this kind of linear combination?
Sorry.
Do you know explicit examples for retail have such that the linear combination is always a question?
Yeah, so that's right. That's an interesting question. So you can actually, okay, so here's a question that people can chew on if you want. So you can actually do this. I said d equals 0 is the case. So you can actually do this on the space of 2 points. So you just have a polymer that just bounces back and forth between 2 points with exponential rates. And I don't even know how to compute the. So in this case, you get Cauchy-distributed marginals, but I don't even know how to compute the two-point function in that case. So I don't know if it has an explicit formula. Or, I mean, you know, it's a solution to some PDE, right? It's, you know, PDE in 2 dimensions, so it's, but yeah, if there's an explicit formula for it, I'd be interested to know.
More questions?
But if you have that linear combination, can't you say in terms of characteristic functions, like, you know, essentially you're computing the characteristic function?
Well, you only compute in the characteristic function in like the positive orthant.
Yeah, for certain values.
Yeah, so
That's
actually
the-
the characteristic function is not analytic. So it's like flat in this orthant. I've done simulations, so it looks like a high school track, but it's like flat on 2 sides and then it like curves on the level sets are flat on 2 sides, which is Cauchy, and then they actually curve on the other side. So it's not Cauchy.
Okay, so let's say.
The lounge will be open if people want to go up and work. It should be, actually, there's some conference going on.
Yeah, no, I'll be interested to know what
Oh, yeah.
Oh, no, that's always, no, I'm right.
Yeah.